Welcome back to the Deep Dive. Today, we're cutting straight to the chase with something really important for a lot of you listening. We're launching into a focused deep dive, one that's really custom-tailored for our CSWIP 3.1 exam prep series.
Yeah, this is key stuff.
Exactly. Our mission today, it's clear. Tackle some crucial multi-choice questions, just like you'll see on the actual exam. And we're going to dissect not just the correct answers, but, the fundamental why behind them. Okay, let's unpack this.
And that why, that's absolutely your superpower as an inspector, isn't it?
Totally.
I mean, this isn't just about ticking boxes on an exam paper. If we connect this to the bigger picture, it's really about building that solid foundational knowledge. That's what transforms you from someone who just sort of knows the answers to someone who truly understands the principles behind them.
Right.
And that understanding, well, that's what you'll rely on every single day out in the field. Diagnosing issues, ensuring safety, guaranteeing quality in real-world welding. It's about knowing why something works or, importantly, why it might fail.
Exactly. So let's just jump right in. That this is your chance to test yourself, see where you stand, and really refine that understanding. Ready for the first one?
Let's do it.
Okay. Question 1. Toe blending is generally carried out. And your options are A, to reduce the possibility of fatigue failure. B, to improve the toughness of the welded joint. C, to increase the ultimate tensile strength of the welded joint, that's the maximum stress before it breaks. Or D, all of the above. So take a second. What's the main goal here? All right, the correct answer is A, to reduce the possibility of fatigue failure.
Yeah, and what's fascinating here is, well, how such a seemingly small detail, right? Toe blending, how it can have such a profound impact on a component's entire service life. Toe blending is basically smoothing out that sharp transition where the weld meets the parent metal.
So instead of a sharp corner.
Exactly. Instead of that almost knife-edge corner, you're making a gentle, gradual curve. Now, fatigue failure, that's not about one single big hit. It's cumulative damage, repeated stress cycles.
Right, over time.
And these failures, they almost always start at points of high stress concentration, a sharp, unblended weld toe. It's like a perfect little stress razor, a tiny notch where cracks can easily start, and then grow under that repeated loading. So by blending the toe, you're spreading that stress out more evenly over a larger area.
Okay.
You're drastically reducing those localized stress peaks, and that, in turn, significantly lowers the chance of fatigue cracks forming and growing. It's a small detail, but with a huge impact on longevity.
That paper analogy, tearing a sharp corner versus a rounded one, that really helps visualize the stress concentration.
Yeah, it's a good one.
But thinking about the inspector out in the field, what's maybe a subtle sign that a toe blend, even if it looks, okay at first glance, might still be inadequate? A potential fatigue risk? Are there specific visual things we should be looking for beyond just an obvious sharp corner?
That's an excellent question because often, it's not the glaringly sharp corner that trips people up. It might be a very subtle, almost imperceptible undercut right at the weld toe. Okay.
Even if the overall profile looks smoother, that slight little gouge, it still acts like a micro notch. It still concentrates stress, even with a blending nearby.
Right.
Another thing is inconsistency. If the blending isn't uniform all the way along the weld, then those unblended or poorly blended sections become the weak points.
Gotcha.
Those are the kind of, nuanced details that separate a quick look from a proper, thorough inspection.
Fantastic insight. Really practical stuff. Okay, let's move on. Question 2. This one delves into specific process controls in TIG welding.
All right, TIG.
Question 2. When considering the tungsten arc welding process, what is the purpose of the downslope control? Options are A, ensure good penetration. B, to prevent arc striking on the parent material. C, to help prevent the formation of crater pipe and possible cracking. Or D, to help prevent tungsten inclusions during welding. So think about what happens right at the very, very end of the weld run. Okay, the correct answer here is C, to help prevent the formation of crater pipe and possible cracking. Right. And this raises an important question. How can a seemingly minor setting on the machine prevent a major defect like cracking?
Yeah.
Think of downslope control in TIG, or GTAW, as a kind of controlled cool down for the weld pool. As you finish the weld, this feature gradually ramps down the welding current over a set time.
Okay.
Now, if you just suddenly cut the arc, stop dead. That molten pool solidifies incredibly fast, like bang.
Right, snap's cool.
And that rapid cooling, that shrinkage, It creates a little depression or even a void right at the end of the bead. That's what we call a crater pipe.
Ah, okay.
And these craters, they're really problematic, not just because they're a dip in the surface, but because that rapid solidification leaves them full of internal stress. So that combination, the geometry and the stress, makes them highly susceptible to cracking as the metal pulls itself apart, cooling. So by slowly ramping down the current, the downslope lets the pool cool and solidify more gently, more controlled. It effectively fills in that crater as it shrinks and minimizes those dangerous internal stresses. So it prevents both the pipe defect and the cracking that often comes with it.
So just to kind of put a fine point on it,
Yeah.
without proper downslope, are we basically building a potential failure point right at the end of every single weld bead, even if the rest of the weld looks perfect?
Pretty much, yeah. It's exactly that. A localized weak spot, almost like an Achilles heel for that weld run.
Wow.
An abrupt stop just creates a ready-made defect, really, just waiting for some stress or load to exploit it later on.
So for you, the inspector, if you're not seeing clear evidence of proper downslope use, maybe you see that distinct crater at the end of TIG welds, that should be an immediate red flag, right?
Absolutely. Immediate flag. It should prompt you to look much closer at that specific area, maybe call for extra checks for potential cracking, high priority inspection point.
Makes sense. Okay, time for question 3. This one tackles fillet weld strength, something that, can often confuse people.
Yes, fillets. Very common.
Question 3, fillet welds. A, the strength is primarily controlled by the leg length. B, the strength is primarily controlled by the actual throat thickness. Or D, both A and B. Okay, think about this one. Which dimension do engineers really rely on for their strength calculations? The critical one, or the correct choice here, it's B. The strength is primarily controlled by the design throat thickness.
Yeah, and if we connect this to the bigger picture, the world of design specs and structural integrity, this distinction is absolutely vital. Fillet welds, they're everywhere, right? Joining parts, often at right angles. So let's just quickly clarify these terms. The leg length, that's simply how far the weld extends along each base plate from the root, how big it looks on the surface.
Yeah, the visible size.
Right. The actual throat thickness is the shortest distance from the root, deep inside the corner, out to the face of the weld. You can measure this with a gauge.
Got it.
But the design throat thickness, that's the crucial one for strength. Imagine it as the narrowest, most critical cross-section through the weld that the engineer is relying on to carry the load.
Okay, the calculated minimum.
Exactly. It's the calculated weakest link that must be strong enough based on the design requirements. It's the minimum effective area that has to resist the stress. So while leg length gives you an idea of size, and actual throat is what you might measure, it's the design throat thickness that dictates whether that weld meets the required strength for the structure. That's the number that ensures integrity.
That makes perfect sense. It's about what's functionally strong, not just what looks big. And as an inspector, here's where it gets really interesting, because theory matters, right? You can see a weld, looks massive, huge leg lengths, looks impressive. But if the fusion isn't right depth down, or the shape means it doesn't actually achieve that required design throat, it won't perform. So when you're on site, what does this mean practically? How do you assess that design throat, not just measure the leg?
Well, it means your inspection has to go beyond just slapping a fillet gauge on the leg lengths.
Right.
You've got to look closely at the weld profile. Is it concave, convex, flat? Because the actual throat achieved can vary a lot depending on that shape, even if the leg lengths are the same.
Okay, shape matters.
Big time.
Yeah.
You need to ensure the weld actually achieves that minimum effective area, that design throat, prescribed by the drawing or the code. This often means really understanding the drawing, recognizing what a proper weld shape looks like for that joint. And sometimes, it might mean calling for NDT if there's any doubt about internal fusion affecting that critical throat dimension.
So what does this all mean? It means knowing the why behind the design, not just measuring the what.
Precisely.
Okay, let's pivot. Let's talk cracking. Always a hot topic for inspectors. Question 4 coming up.
All right, cracking types.
Question 4. A crack type most associated with the submerged arc welding process is A, hydrogen cracking in the HA&E, that's the heat-affected zone. B, solidification cracking. C, lamellar tearing. Fatigue cracking. Think about SAW, submerged arc, its unique characteristics. Heat input, cooling. And the correct answer is B, solidification cracking.
Yeah, and what's fascinating here is you really see how the process parameters directly influence the type of defect you're likely to find. Submerged arc welding solidity, it's known for very high heat input, really deep penetration, big weld pools, and it all happens under that blanket of granular flux, right?
So that gets
Exactly. Now, these characteristics make it super efficient, great for heavy stuff, but they also create conditions that make it particularly prone to solidification cracking.
Okay, why specifically that type?
Well, solidification cracking, or hot cracking, it happens while the weld metal is actually solidifying, not afterwards when it's cold. It happens because certain things, impurities like sulfur or phosphorus, tend to have lower melting points. They're the last bits to freeze as the weld pool cools.
Right.
So as the main bulk of the weld metal solidifies and shrinks, these low melting point liquids get trapped between the solidifying grains, and they get pulled apart by the shrinkage stresses, forming cracks right along those boundaries.
Ah, I see. They create weak paths.
Exactly. And because SAW has these large, deep pools that cool relatively slowly under the flux, there's just more time and opportunity for these impurities to segregate and for significant shrinkage stresses to build up across that mushy, half-solidified metal. That makes it more prone to this specific defect compared to many other processes.
So as an inspector, if you know a component was made using SAW, does that automatically change your approach? Do you sort of put your solidification crack glasses on?
Absolutely, 100%. Recognizing those associations, process to defect links, that's a hallmark of a good inspector. Okay. If you know it's a SAW, your radar for solidification cracking should immediately go way up. You'd focus your visual checks and maybe NDT, like dye pen or MAG particle, specifically looking for those telltale signs. Often they appear as cracks right down the center line of the weld bead.
Right in the middle.
Yeah. Knowing the process helps you anticipate the likely problems, allows for better prevention during welding, and more targeted, effective inspection afterwards.
Makes total sense. Okay, our final question for this deep dive. Back to process control, selecting the right tool for the job, or the right mode in this case.
MIG-MAG modes, important stuff.
Question 5. When considering the MIG-MAG welding process, which the following metal transfer modes would be the most suited to the welding of thick plates over 25mm flat welding position? Options A, dip transfer .B, pulse transfer .C, spray transfer D, globular transfer. Okay, think about welding really thick plate, heavy stuff. What do you need most from the process? All right, the correct answer for question 5 is C, spray transfer.
Yeah, and if we connect this to the bigger picture, selecting the right tool for the job, understanding metal transfer in MIG-MAG, or GMAW, is essential. So MIG-MAG uses that continuous wire feed. When you're welding thick plates, say over 25 mils, especially flat, your main needs are high deposition, getting a lot of metal down quickly, and deep penetration.
Right. Need that heat.
Exactly. And that's where spray transfer really shines. In spray transfer, you're using high voltage, high current. And this creates a stream of really fine, tiny molten metal droplets shooting across the arc. It's literally like a spray, delivering intense, focused heat right where you need it.
Okay.
So this mode gives you high heat input, great penetration, and a really stable arc. All ideal for heavy sections like that.
And the others? Why not them for this job?
Well, briefly, dip transfer. Much lower heat input. Good for thinner stuff, or maybe welding at a position where you need a cooler puddle.
Right.
Not enough punch for thick plate.
Right.
Globular, that's kind of messy. Less controlled, bigger, irregular blobs of metal falling across the arc, lots of spatter. Not ideal for high-quality, heavy work.
Gotcha.
Pulse transfer offers great control. It's very versatile. But for just sheer power and efficiency on thick plate in the flat position, spray is often the go-to choice.
Okay, so here's where it gets really interesting for the inspector on the floor, right?
Yeah.
You walk up, see someone welding a 30mm thick plate, flat position, but the machine settings, the sound, it clearly looks like dip transfer.
Alarm bells.
That's got to be a major red flag for lack of penetration, hasn't it? What's the immediate thought process?
Your immediate thought should be, whoa, insufficient fusion, lack of penetration, almost guaranteed. If the process mode isn't putting enough heat and metal deposition down for that thickness, you're looking at a weld that's just not structurally sound, period. You'd expect it to look maybe okay on top, but underneath. Probably poor root fusion, maybe incomplete penetration. It comes back to knowing the optimal process for the application. Okay. Any big deviation like that, it needs immediate investigation into the actual weld quality.
Fantastic. And just like that, we've unpacked 5 really critical concepts, vital for your CSWIP 3.1 exam, definitely.
Yeah.
But honestly, just fundamental for your career as a welding inspector.
Absolutely.
We covered toe blending and fatigue, TIG downslope, the difference between leg length and design throat thickness for fillet strength, the link between saw and ubia and solidification cracking, and picking the right MIG-MAG mode for thick plate. Each one isn't just an exam point. It's a piece of the puzzle for ensuring safe, reliable welds. So really take some time, review these, think about how they apply when you're actually looking at a weld.
Indeed. And remember, this deep dive, and the exam too,
Yeah.
it's not just about memorizing facts, is it?
No.
It's about building that holistic understanding, the principles. When you really grasp the why behind each answer, you're not just prepping for a test, you're empowering yourself. Empowering yourself to make informed, critical decisions when you're faced with real-world situations, maybe challenging ones. And, this raises an important question, something to think about. How might a deeper understanding of these seemingly small details, these process controls, these defect types, how might that ultimately impact the safety and reliability of the really big, important structures you might be responsible for inspecting one day?
That is a fantastic thought to leave everyone with. Really underscores the importance of this knowledge. Thank you for joining us on this deep dive into these welding inspection essentials. We wish you the very, very best of luck with your studies. Keep digging into that why, and we look forward to the next one.